We had page 209, questions number 1 and 2 due for homework today. I want to take a look at question number 2. It's the more challenging of the two for sure. And this is the one that we didn't talk about how to do per se. We've talked about all the concepts that you need to know in order to solve this question, but we've never actually put them together in the context of a question like this. So let's see what we can do with this, okay? It says during the first quarter phase of the moon, Earth, the moon, and the sun are positioned as shown in 4.22. We want to find the net gravitational force exerted by both the moon and the sun on the Earth. Well, so we draw a free body diagram. We know that we have two forces acting on the Earth. We have the sun acting on the Earth, pulling it this way. Right? The Earth is attracted toward the sun. We're going to call that FSE, the force of the sun on the Earth. The moon pulls the Earth this way. My guess is with a significantly smaller force, but if you draw that force just as big as the other one, I can live with that because we're not really sure exactly what the forces are going to be right now. Okay, I'm going to draw it shorter because I'm pretty sure it's going to be a smaller force. We're going to call that FME, the force of the moon on the Earth. Now the sun gets pulled towards the left towards the Earth, and the moon gets pulled downward towards the Earth, but we don't really care what happens to the sun and to the moon because that's not the question. The question is what happens to the Earth. So we calculate now the value of FME and the value of FSE. This is going to be GMME over R squared. So we're going to say 6.67 times 10 to the minus 11 times the mass of the moon. What was the number for the mass of the moon? I don't remember that. 7.35 times 10 to the 22 kilograms, thank you. And the mass of the Earth, I think, was 5.97 times 10 to the 24. We're going to divide that by R squared, and the distance here, 3.84 times 10 to the 8. Don't forget to square that. Emma, what do you get when you do the math there? 1.9848 times 10 to the 28 newtons times 10 to the 20 newtons. That's a big force, but it has to be, right? The moon is heavy. It's a lot lighter than the Earth. It's a lot lighter than the sun, but it's still heavy. And it's hurtling through space, and it wants to go in a straight line because that's what things want to do, is go in a straight line. Newton's first law tells us they want to go in a straight line. But it doesn't go in a straight line, so there has to be a force that keeps it from going in a straight line, an unbalanced force. That unbalanced force has got to be a big one, because to keep something so heavy with so much inertia from going in a straight line, you need a really big force. It's 1.9848 times 10 to the 20 newtons. Now let's get the force of the sun on the Earth. This isn't any different than question number 1 yet, is it? Free body diagram, calculate each of the forces. This is going to be G times the mass of the sun times the mass of the Earth over R squared. It's going to be 6.67 times 10 to the minus 11 times the mass of the sun, which is, I want to say 1.98 times 10 to the 30. Or is it 1.99 times 10 to the 30? 98? And then? Thank you. And the Earth is, again, still 5.97 times 10 to the 24 kilograms. Okay, we divide that by the distance here now, which is quite a bit bigger, 150 million kilometers. 1.50 times 10 to the 11 meters. Don't forget to square that. My guess is I'm going to get a bigger force here, quite a bit of a bigger force here. What do you end up getting for this one? David, you got that one? Force of the sun on the Earth? Okay. Sonia, you got that? Exactly 3.5? Okay. Anybody have the unrounded number? Julia? Times 10 to the 22? Thank you. We want to use that unrounded number, right, until it's a final answer. If the question said, what's the force between the sun and the Earth, then you'd round it. But if it says, what's the net force, the combined force, then we have to use the unrounded number. All right. What am I going to do now to find that net force? What's my next step? Your hint is you know this, right? You've done this a million times already this year, just not in this context. You have a free body diagram drawn. Don't we want to say F net is equal to the sum of the forces? Not this time. because we're in 2 dimensions. So this time we have to draw a picture, another picture, not a free body diagram, but this time we have to draw a vector diagram. It's going to look something like this. 1.9848. No, the horizontal force is going to be 3.5218. That's 10 to the 22. And the vertical force, the force of the moon on the Earth, is going to be 1.9848 times 10 to the 20. And we're going to combine those to find the resultant vector and the angle. The resultant vector is going to be found by the Pythagorean theorem, and the angle is going to be found by the inverse tan function of opposite over adjacent. All right, this side of the room, next side of the room over, you guys find the angle, please. And this side of the room, Fraser's side and over, you guys are going to find the hypotenuse there. Yeah. 0.3 degrees. Anybody else get that? Should be rounded to how many digits? So 3 digits. 323. And it would be north of, you know what? Let's not say north of east here, because we're in space, right? There is no north in south and east and west, right? Let's just say 0.323 on our picture, on our diagram. Now, I'm not sure why they rounded that to 1 digit, actually. The 0 is not significant because it's a leading 0. The 3 is, it's a trailing 0. So that's only 1 digit. I'm not sure why they did that. That should be a 3-digit answer, 0.323 degrees. What do we get for R here over on this side? Taylor, do you got that? Anybody else get 3.52? Yes? Okay, so let's go through that then, just to make sure that you can get the right thing here, okay? So we're going to say it's 3.5218. 3.5218 times 10 to the 22 squared. We're going to add to that 1.9848 times 10 to the 20 squared. Now let's square root all that. Taylor, is that making sense so far? We end up getting 3.52. Yeah, 3.52 times 10 to the 22. All right. So we spent a day now going over how to find the force of gravity that acts between these two objects. This force of gravity that explains not how the Earth revolves around the sun, but rather why the Earth and other planets revolve around the sun. And in the equation that we use to solve those problems, we've used a constant. We called it the gravitational constant, 6.67 times 10 to the minus 11. But we haven't established where that came from, where that number came from. I'm going to tell you real briefly here now about an experiment that was performed by a guy named Cavendish that's going to tell us what the value of that constant is. We know the value of the constant now, right? But we're going to describe the experiment that he used to find the value of that constant. Now, keep in mind as I do this, it's a bit of a simplification, what I'm about to show you, but it is essentially correct, essentially what Cavendish would have used to find that constant. So here's the way it starts out. You got a ceiling or a roof or the top of a box or something, okay, that provides us with an anchor. And then you got a string hanging down from that ceiling. And then you got a rod on the end of that string that has got a couple masses, one on either end. We'll call this mass 1, and we don't really care what this one is called. Okay? It's just another mass to balance it so that it doesn't tip over, literally. So we got one mass there that's attached to a rod that's on the end of a string. Now mass 2 is another mass that I'm going to bring nearby mass 1. It's going to be represented by, as you're watching me, by my fist. So mass 2 is coming towards mass 1, represented by my fist or represented by the second object there in the diagram. as mass 2 comes nearby mass 1, there's going to be an ever so slight force of attraction that acts between those two. And all of a sudden, mass number 1, ever so slightly, will start moving towards mass number 2. Now, what are we going to do to figure out the constant from this? We've got to measure some things. The first thing we're going to measure is the value of M1. We can do that easily, right? The value of M1 can be measured with a scale. M2, same deal. We can measure that easily. R, the distance that separates object number 1 and object number 2. We can measure that relatively easily as well. If we want to find the value of G here, though, the gravitational constant, we need these 3 variables and also the force of gravity. That's a harder one to measure. You can't just take some scale and measure the force of gravity here because it's so small. I want to take you back to your childhood, though, your recent childhood. It could have been as early as or as late as yesterday. When you guys go to the park, you go to the park, hang out on the swing set. Sometimes when I drive by Morris Gibson School, I see teenagers sitting on the swing set playing, messing around on the swing set, probably smoking, because that's what all teenagers do, right? When they hang out, you know, at school when school's not in session, they smoke or something. You guys wouldn't do that though. So you're on the swing set, you're swinging back and forth, and then you decide. I don't know about you, but when I was a kid, I used to do this all the time. I'd start twisting the swing set. You twist it as far as you can twist it so that you could let it go and start spinning around really fast. Enjoy it while you can. Okay, when you're my age and you start spinning around, it takes about 2 revolutions around to start getting dizzy. When you get old, you get dizzy really, really fast. I was on that, you know, those tire swings that you can spin around really easily, you know what I'm talking about? I was on one of those at Morris Gibson one day. My 5-year-old was twisting me around, and I said, you got to stop. I'm going to get sick. My 5-year-old was twisting it around, and I was going to get sick. When you get old, you get dizzy quick. Anyways, so you're on that swing set, and you're twisting it because you want to spin faster and faster and faster. You guys know intuitively that when you twist that swing set, you guys know that it takes more force to twist it the further you go, right? You twist it just a little bit, okay, it requires some force. But you twist it a little bit more, it requires more force. You twist it even more, it requires even more force. The more you twist it, the more force it requires. You could, if you wanted to, perform an experiment that would measure how much force was required to twist that swing set a certain amount, so that the next time you twisted it 37 degrees, you would know that required 721 newtons of force, or whatever the case may be. Make sense? Twist it 87 degrees, then it requires this much force. You could create a little table that says, twist it this much force is required to do that. That's what Cavendish would have done, essentially, is said, look, I know by the torsional properties, torsion means twisting, by the torsional or twisting properties of this string, I know that if it twists this many degrees, then it required this much force. Or if we twisted it that many degrees, it requires that much force. From that, we can measure, kind of indirectly, right? We can measure the value of the force of gravity there. Now that we have the values of M1, M2, R, and Fg, and once we've performed this experiment dozens of times, then we can take the equation that Newton had already come up with, gm1 m2 over r squared, rearrange it to solve for g. R squared goes up by multiplying, m1 m2 goes down by dividing, g becomes equal to Fg times r squared over m1 times m2. So we've got the value of g, not as a direct measurement, but by simply measuring other things, the value of the force by the torsional or twisting properties of the string, the value of r, the distance separating them, which is easy, m1 and m2, which is easy, and then plugging them into that equation and solving for this. Do it a dozen times, average them out, see what you get. I want you to work on these questions for the remainder of class and for homework this weekend. Page 215, number 1 and 2, and 4 to 7, please. So 6 questions between the next 7 or 8 minutes of class and the 48 hours of weekend that you have to work on homework.